Imagine you have two identical molecules of benzaldehyde. On their own, they are relatively simple structures, just a benzene ring attached to a carbonyl group. They'd happily float past each other in a flask forever. But if we add a tiny amount of potassium cyanide, something remarkable happens. These two identical building blocks suddenly snap together, creating a beautiful, larger molecule called benzoin. But why? Why does adding a salt like cyanide cause two molecules that usually ignore each other to bridge a new carbon-carbon bond? To understand this, let's look closer at the benzaldehyde molecule. Notice the carbonyl carbon, the one double bonded to oxygen. Because oxygen is greedy for electrons, it pulls density away from that carbon, leaving it with a partial positive charge. Normally, this carbon is an electrophile. It wants to be attacked. But here's the problem. To link two of these together, one of them has to act as the attacker. We need one of these carbons to stop being positive and become negative. We need a chemical umpire to flip its personality. Enter the cyanide ion. Let's visualize the first step. The cyanide ion is a powerful nucleophile. It seeks out that positive center and strikes the carbonyl carbon. As it bonds, the double bond to the oxygen kicks up, creating an intermediate. Now look at the hydrogen atom still attached to that central carbon. Typically, that hydrogen is very difficult to remove. But because the cyanide group is now attached, and cyanide is incredibly good at pulling electron density toward itself, that hydrogen becomes much more acidic. A base in our alcoholic solution can now swoop in and pluck that proton away. And here's the key insight. The moment that proton leaves, the central carbon gains a negative charge. It has been transformed from an electrophile into a nucleophile. This is what chemists call unpoling, or a polarity reversal. The cyanide has effectively performed a catalytic brain transplant on our molecule. Now that we have this negatively charged intermediate, it's ready to hunt. It looks around and finds a second, untouched molecule of benzaldehyde. Watch what happens when they collide. Our activated carbon attacks the carbonyl carbon of the second molecule. Just like that, the new carbon-carbon bridge is formed. We're almost there, but the bridge is a bit messy. Oxygen atoms are trading protons, and we have a negatively charged oxygen sitting right where we don't want it. However, the cyanide ion, having done its job of activating the first molecule, is now ready to leave. As the oxygen reforms its double bond, it kicks the cyanide group back out into the solution. The cyanide was never consumed. It was a ghost in the machine, facilitating the union and then disappearing. What's left behind is benzoin, a perfectly formed alpha-hydroxy ketone. So, the next time you see a complex molecular coupling, remember the benzoin condensation. It's a masterclass in how a single catalyst can temporarily flip the fundamental nature of a molecule, turning a passive target into an active hunter, all to build something more complex than what we started with.